Welcome to my presentation on micro-splatting, maximizing isotropic constraints for refined optimization in 3D Gaussian splatting. I'm Jeewon Lee from MEIC Lab, SUNY, Korea. Before I dive into the paper, I would like to briefly introduce on the problems that we face today and how this paper has potential to address them. In hazardous environments like ship engine rooms or nuclear power plants, inspections are risky, costly, and infrequent due to limited accessibility. Robots like drones and swimmers help, but they still suffer from limitations like battery life, weather, and insufficient detail capture. Digital twin technology combining 3D reconstruction with sensor data is emerging as a powerful solution for remote inspection. We've evolved from LiDAR and structure for motion to NERF and now 3D Gaussian splatting, which offers real-time rendering and high visual fidelity. But even with 3D Gaussian splatting, fine details like cracks and corrosions can be lost due to the way splats behave, especially in high-frequency areas. This happens because current adaptive densification strategies often represent fine textures with oversized splats causing blur. Gaussian splats are inherently low-pass filters. They suppress high-frequency signals, which means fine textures get blurred away in the final output. To tackle this, we regularize the covariance to keep Gaussians compact and introduce adaptive densification where high-frequency content exists. In short, we make splats smaller, more spherical, only in the areas that need it, and ensure no gaps in the reconstruction. Micro-splatting builds on 3D Gaussian splatting by integrating these new strategies directly into the existing pipeline, preserving its real-time capabilities. We begin by initializing Gaussians from the structure from motion point clouds. Each Gaussian has attributes like position, color, shape, and opacity. To render, we project these Gaussians into the camera view by transforming their 3D covariances into 2D image space using the Jacobian. Multiple Gaussians can overlap a pixel. Our renderer sorts them by depth and blends them front to back to compute the final color. We then prune the low opacity splats and split overly large ones if they cause reconstruction error, fine-tuning the splat placement. During this stage, we added 3 techniques. First is the covariance regularization. We measure the spread of each Gaussian through the trace of its covariance matrix. When it's too large, a penalty is applied to shrink it. By measuring error gradients, we detect where more detail is needed and split Gaussians accordingly to increase local fidelity. We also enhance the loss function by combining L1, L2, the SSIM, and covariance penalties for stronger supervision of fine structures. Our method concentrates more small Gaussians in detailed regions, especially in the high frequency and high gradient areas as seen in the splat radius plot. Also, this is further observed in the splat cardinality table where it shows the count of Gaussians in each bin with different radii. Bin 0 contains the smallest size Gaussian where the size increases to bin 9. Quantitative results show that micro-splatting outperforms baselines like NERF and even 3D Gaussian splatting in the PSNR, SSIM, and LPIPS scores. Across various scenes, our method maintains sharper edges and textures, though it does introduce slightly more computational load. Micro-splatting improves detail in complex scenes, but this comes at the cost of increased splat count, especially in textured regions. While training time stays comparable, rendering requires processing more splats per frame, slightly reducing the FPS. Removing our key components significantly degrades performance, validating the importance of each part. Side-by-side, visualizations further show that micro-splatting maintains crisp textures and clear geometry. To show that it is generalizable in other custom dataset, here is a model of SMR reactor core model that was collected by ourselves, and it is shown that the details such as the bolts and the texture of the outer space is preserved better than the original 3D-GS. We preserve detail with isotropic constraints and smart densification strategy, but there is a trade-off between the quality and rendering frame per second. Also, results rely on good structure from motion input. Thank you for watching. This was Micro-Splatting, making 3D Gaussian splatting more accurate and inspection ready.